Okay, so previously we were looking at oxidation numbers and how to assign oxidation numbers for elements in a compound, and so now we're going to talk about oxidation reduction reactions. Okay, so oxidation reduction reactions are reactions in which elements are undergoing a change in the oxidation number. So you should be familiar with what oxidation numbers are. That's what we did in the previous exercise. And so what is oxidation? By definition, it's an increase in oxidation number. Reduction is a decrease in oxidation number. So here we're going to look at the different types of redox reactions. The first type is what's called a combustion reaction. Okay, so we should be very familiar with combustion reactions. For example, we all drive to work and we use an internal combustion engine, and so that you have combustion reactions happening all the time. That's why you use gasoline to fill up your car, because your engine runs on gasoline, and that gasoline is used as fuel. Okay, you also have an air intake in your engine, and so you have to have oxygen in order to burn that fuel, and you end up with different products. With hydrocarbon combustion reactions, your products are usually carbon dioxide and water. And depending on what your fuel happens to be, sometimes you're going to have a mixture of your products. So here's an example of solid rocket fuel reaction. Here we have aluminum and solid rocket fuel that's going to react and produce these products. So the fuel is going to be the reductant, and the oxidant is going to be oxygen. Not all the time, though. In this case, it's shown here, and often light in the form of a flame. So your products, you're giving off energy in the form of light, and usually heat as well. And so, combustion reactions are very common. And so, if you look at the oxidation numbers, they're changing. So, for example, aluminum has an oxidation number of 0 because it's an uncombined element. Okay, and then here in this compound, splits apart into two different elements. Okay, so two different compounds, sorry. And so its oxidation number for aluminum here in this case, so oxygen is -2, -2 times 3 is -6. And so aluminum has to be +6 divided by 2, because there's 2 atoms there. So aluminum has to be +3 in this case. So aluminum went from an oxidation number of 0 to +3. And so in that case, it is being oxidized. Okay, and in this compound here, we have aluminum and chlorine. Chlorine is -1 times 3, it's -3. So aluminum's +3 here. Okay, so here again, going from 0 to +3 for its oxidation number. So with redox reactions, basically the oxidation number changes. Okay, and in other reactions, the oxidation number does not change. So that's what makes redox reactions sort of special, in that you have basically electrons being transferred during the reaction. All right, so a lot of times with redox reactions, when we're doing them in the lab, when we're doing experiments in the lab, a lot of times you're going to see single replacement reactions. Okay, and again, single replacement or single displacement, just like we talked earlier about double displacement or replacement reactions, either word you want to use is fine. So generally you're going to have, with single replacement reactions in general, the reactants are going to be some sort of single element here. Okay, usually it's a solid, and then you have a compound. So one element in a compound, and that one element is going to replace another. So depending on what that element is, in this example we have copper solid, okay, and then we have silver nitrate. And so the copper, the metal, is going to replace the other metal. Okay, you're never going to see a situation where the metal is going to replace two nonmetals, all right, or a nonmetal in general, because that just doesn't happen for the most part. And there are exceptions, of course, because this is chemistry, but for the most part, you don't see that. So when you see a metal here, it's going to replace the other metal. So copper is going to replace silver in this reaction. That's what you see here. It's called single replacement because basically you have a single element replacing another. Okay. So here, if we look at the oxidation numbers, we can see copper is uncombined by itself, so it would have an oxidation number of 0. And then going to your product side, here, nitrate overall is -1. There's 2 of them, so that's -2 here. So copper must be +2 here. So it's going from an oxidation number of 0 to +2. So copper is being oxidized in this example. Okay. Now let's look at the other metal, this and silver nitrate here. What happens to silver? So nitrate has an overall charge of -1 as a polyatomic ion. So silver must have a +1 charge here. So you have an oxidation number of +1 going to 0. Silver is 0 here because it's an uncombined element. So +1 going to 0, that's reduction. Okay. So here we see copper being oxidized, silver being reduced. Okay, in general, that's going to happen when one metal is oxidized, the other is reduced, or vice versa. Okay, so you're not going to see both of them being oxidized or both of them being reduced. All right, so here's a picture of what's cool about single replacement reactions is it's actually one of the ways you can plate things. Like, for example, if you've ever bought jewelry and it was gold plated, that's basically you're just using some replacement chemistry that's going on with that. So, for example, here we have a copper wire. And we can place the copper wire in a solution containing silver. The silver is going to replace the copper, okay, just like in the reaction we saw, and produce a solid silver. And so the silver is going to plate on the outside of that copper, okay, and then whenever we have the copper in solution, you're going to see that anytime you have copper in, well, I would say copper sulfate, for example, is this beautiful blue color, and that's what you're seeing here. When copper is in solution, it's usually a nice dark blue color. So that's what you see here when you see the silver that's being precipitated and it's being plated onto this copper ring, and the copper is going into solution and becoming aqueous. And so that's what we saw in the previous example. The copper is going into solution and the silver is plating onto the copper, or replacing the copper basically. And so that's what you're seeing here. And eventually, if this is a solid piece of copper, you would expect this little coil to break down because it's going into solution, and then you're just going to see some silver at the bottom of the test tube. So this sort of just represents what we saw as a written reaction here. All right, so talking about redox reactions, and we have to learn how to balance them. Okay, so redox reactions here, we're going to balance them using the half reaction method. So this is a very long process, and so we're going to go through this. I'm going to show you it in 2 different ways. I'm going to show you what the slides show, and then I'm going to do it by hand, so I sort of break it down for you so you can kind of understand sort of the thinking process involved when you're trying to balance out a redox reaction. So redox reactions do take place in aqueous media, and so aqueous media means so it's going to involve a solution where water is the solvent, and so when water is the solvent, you have an excess of hydronium ions. So hydronium ions are H3O plus, and hydroxide ions, which are OH minus ions as reactants and products. So those are always going to be there because it's a solvent. So there's a lot of them around. So although the species are not always oxidized or reduced, so they're talking about the water molecules, the hydronium ions and the hydroxide ions, they do participate in the chemical change in other ways. So the reactions are difficult to balance by inspection. Okay, so before we balance chemical reactions by looking at just the simple coefficients and the subscripts and making sure we had the same number of hydrogens, for example, on both sides, or oxygen atoms on both sides, redox reactions are more complicated. They involve a lot more species other than just number of atoms. Okay, so we have to use a different approach in order to balance redox reactions, and we use what's called the half reaction method. All right, so there are several different steps, and actually there are more than 5 steps. I think there are 7 steps total to balance out a redox reaction. So here are the first 5. Right, 2 individual half reactions, the oxidation and reduction reaction. So you have to first take the reaction and break it down and figure out which element's being oxidized and which one's being reduced. Okay. Then you have to balance all the elements except oxygen and hydrogen, and then balance the oxygen atoms by adding water molecules, balance the hydrogen atoms by adding H plus ions, and balance the charge by adding electrons. All right, so those are actually 5 steps, and then so after that, then you have to, step 5 would be to multiply the reaction, each half reaction by a coefficient by the smallest possible integer to yield a equal number of electrons in each, and then add the balanced half reactions together and simplify by removing species that appear on both sides of the equation. So depending on whether your solution is, if it's acting as an acid or it's acting as a base, and the problem will tell you which one it is, if it's an acidic or a basic media. So for reactions that are occurring in a basic media, which means that has excess hydroxide ions, you're going to carry out this additional step of adding hydroxide ions to both sides of the equation, and the numbers equal to the number of H plus ions. All right, on the side of the equation that containing both H plus and OH minus ions, combine these ions to yield water molecules. Simplify the equation by removing any reductant water molecules. And then finally check to see that the number of atoms and the total charges are balanced. So there are a lot of steps involved in balancing redox reactions. It's not too difficult once you start to do some practice. Okay, so practice is the key here when you're trying to balance redox reactions. So it requires a lot of different skills. So let's go through the first step here. So we see here with this first slide, we see a balanced equation that we're starting off with. Okay, so we have a dichromate ion, an iron 2 ion, and it's yielding chromium 3 and an iron 3 ion in acidic solution. So notice they're specifying whether the solution's acidic or basic. And that's important because if it were basic, then we would have to add the hydroxide ions after we added our hydrogen and water molecules to balance out oxygen. And so here it's an acidic solution, so we don't have to do that step at least. But the first thing we're going to do is figure out how to write the half reactions. So let me go, here it's showing you, but I want to show you how you do it. If you were to do it on paper, okay, so here we see the overall reaction. So for a half reaction, this is what I'm going to first do. I'm going to kind of figure out what elements go together. So we have chromium here and oxygen, then chromium. So I'm looking for the oxidation number of chromium to see if it changes. Okay, and then we have iron here and iron there. So again, I'm going to look for any changes in oxidation number for iron. Well, it's pretty obvious here. Iron went from +2 to +3. Okay, so it went up in oxidation number. So that means it was oxidized. Okay, and then for chromium, here I have to figure out its oxidation number. So overall, it has to add up to -2, right? All the oxidation numbers. So I know oxygen is -2, so 7 times -2, that's -14. So this has to be positive 10, right? Because, not 10, sorry, 12. Positive 12, and so 12 and -14 is -2. And because there are 2 atoms here of chromium, it's not going to be 12, this is 12 overall, but per atom it is going to be +6. Okay, so chromium went from a +6 to a +3. So it became reduced. Okay, all right, so let me go ahead and write my half reaction. So I'm just going to put these guys together. So Cr2O7, so the dichromate ion there, okay, and then it yields chromium 3 plus, okay. I'm going to go ahead and write out what it is, okay, so I know that chromium was reduced, okay, and then my oxidized species here is iron. Okay, so that's what my half reaction looks like. Right. So and that's what they have here. Now generally they write oxidized before they write reduced, but it doesn't really, technically doesn't really matter. All right, so here, step 1, write the half reactions. We did that on paper. Next step, balance all the elements except oxygen and hydrogen. Iron, the half reaction is already balanced here. So here for chromium, if we look, remembering how to balance chemical reactions, we're just looking at the number of irons on both sides. We have 1 on both sides. Here we have 2 chromium atoms, and we only have 1 there. So I need to put a 2 there to balance out the chromium. Okay. Remember, we're going to leave oxygen later. We're not going to balance it at this point. Okay. So next step is to balance oxygen atoms by adding water molecules. All right. So here, looking at my reaction again, I have 7. I have no water molecules or I have no oxygen for the iron reaction, but I have oxygen here. I have 7 atoms of oxygen here, so I need 7 atoms of oxygen there. So the only way I can balance it is to add H2O or water. So now I have 7 oxygen atoms. Okay, so that's step 3. Step 4, we're going to balance the hydrogen atoms by adding H plus ions. So going back to my equation here, so here I have 7 times 2, which is 14 hydrogen atoms on the right hand side. So I need 14 hydrogen atoms on the left hand side. All right, so now I have 14 hydrogen atoms. I'm balanced now with my number of hydrogen atoms, which you see there. All right, now I have to balance the charge by adding electrons. All right, so let me go ahead and so I need to balance the charge by adding electrons. So if you look at your oxidation numbers here, you can see that. Let me all right, so I went ahead and rewrote this because it was kind of getting cramped up here. So here's my reactions. So the next thing we need to do is balance out the charges by basically adding electrons. So if we look here, we have this oxidation reaction. So what happened, iron went from +2 to +3, so it lost an electron, okay? So it lost 1 electron per atom. Here we're only dealing with 1 atom of iron in this case, so it's just +1 electron here as a product, because it lost the electron. Now, when it becomes reduced, it gains the electron, so the electron is going to be on the reactant side. So if we look at our oxidation number here for chromium is +6, and as a reactant and as a product it's +3. So it lost 3 electrons, it gained 3 electrons for every atom. It went from +6 to +3. So that means that it gained 3 electrons, so +3 here, but notice we have more than one element. All right, so we have more than one atom here. Here we only had 1 atom. Here we have actually 2 atoms of chromium. So 3 times 2 is actually 6, so it's going to be +6 electrons. All right, so that's going to be the number of electrons that are gained by 2 chromium atoms in this reaction. Okay, so it's not +3 in this example, it's +6, and that's because there are 2 atoms of chromium and not 1. Here there was only 1. All right, so that gives us to step 5. And then step 6, we multiply the 2 half reactions, so the number of electrons in one reaction equals that of the number of electrons in the other. So what we have to do here, if we look at our electron number here, here we have 1 and here we have 6. So what we need to do is multiply. Sometimes you have to multiply both half reactions. So for example, if this were a 2 and this were a 3, right, it would be 3 and 2. So sometimes you have to multiply both reactions if you have an even and an odd number issue here. This is an odd number here, but we only have to multiply this one reaction because we want to make sure we have each reaction has the same number of electrons, whatever that number happens to be. In this case, we need both reactions to have 6 electrons. Okay, and so the strategy for this is whenever we're basically finishing up our reaction, we have to be able to cancel out the number of electrons. So that's why we're going through this process. All right, so I have to rewrite this reaction now. And so my oxidized species is 6 times iron plus 2, so 6 Fe2 plus 6 Fe3 plus 6 electrons. Okay, and then my reduced reaction doesn't change, so I just rewrite what was there initially. 14H plus, and this reaction is getting longer and longer. Okay, so there we go. So now we have this reaction, and this is what it looks like when it's nice and typed up. Okay, so we've multiplied the half reaction so that the number of electrons are going to be able to cancel out, basically. All right, the next step, step 7, add the balanced half reactions and cancel out the species. So now we're going to actually make it one big long equation, okay, and try to cancel out the species. So when I do that,